Hello everybody, so this is the nuclear chemistry part of the quiz 4 review and mid-semester review for AWC's General Chemistry 1. So let's look at this, the nuclear chemistry. Draw a general nuclear band of stability. So it's going to look like this. We have protons on the bottom, neutrons on the top. We've got our nuclear band of stability inside of here. At 83, the type of radiation, or rather the type of radioactive decay that it could go under if it's not in the nuclear band of stability, it's going to be alpha. If it's above this nuclear band of stability, if we plotted it using our number of neutrons and our number of protons, it's going to be beta negative. If it's below it but not past our protons number of 83, it's going to be beta positive or positron. That's our general nuclear band of stability. So now let's determine the types of decay that each of the following isotopes will undergo and whether or not it's above or below the band of stability. We can also find the neutron to proton ratio, and we're going to do that to the thousandth decimal place. So let's look at berkelium, or berkelium. It was discovered, I believe, if I remember correctly, at UC Berkeley. There we have berkelium. So we know that this has 97 protons. Using this 230, we also know it has 133 neutrons. So if we had a written in nuclear band of stability, we could plot it, but let's first find the neutron to proton ratio. That's 133 over 97. It's going to be equal to 1.37. So if you want, you can look up a nuclear band of stability, or you could look up the neutron to proton ratio for berkelium. But I'm going to tell you right now that this, I can just sort of eyeball this, that this is going to be past, so we know it can't even be beta, and it's going to be past this. And because it has a high number of neutrons, it could be either alpha or beta minus, or just beta. Because once you get up to here, it could be shooting out both types of particles. So this is beta minus, or just beta, and alpha. That's the type of decay. And it could be, again, above or below, depending on what type of decay it undergoes, because it is at such a high level. Let's look at tellurium-145. So tellurium has 52 for its atomic number. So then that means we have P plus is equal to 52. Our neutrons are equal to 93. And so our N over P plus ratio is equal to 93 over 52. This is 1.788. Okay. So if we had it, we would know it couldn't be alpha, but because our neutrons aren't that high up, we're going to know are high up, but it falls pretty steadily right here in the beta plus minus or beta area. And again, I highly encourage you to look up a nuclear band of stability and use that one. It's going to be beta, just plain old beta. And this is above the band of stability. Now, germanium-70. It's got an atomic number of 32, and this is germanium-70. So we're going to say our P plus is equal to 32. Our neutrons are equal to 38. Our N over P plus ratio is equal to 38 over 32. And this is about 1.1875. And let me go back and I'll give it to the thousandth decimal place. But let me just finish this one quickly. And then, so it's under the protons. It's not that high that it would run into the neutrons. This is actually positron, or B+, and this is below. Now, since I asked you to give these to the thousandth decimal place, this goes tens, hundreds, so let's actually do this calculation so that we get it to the thousand. So 133 divided by 97 is equal to about 1.37113. To the thousandths, that's 1.371. Final answer for that one. For this one, 1.788, tens, hundred thousandths. That's the good one. This one, 1.1875. Well, we don't need this 5, so let's call it 1.188. That's our final answer, to the thousandths. Let's go to the next page. If a radioisotope has a half-life of 112 days, what percentage of radioisotope remains after 2 years have passed? Well, let's find out in those 2 years how many half-lives have undergone. So in 1 year, there's 360 days. So 2 years, that's 720 days. So we'll divide that by the half-life, 112 days, which is equal to the half-life, so 720 divided by 112 is equal to about 6.43 half-lives have undergone. So let's use the equation. T1/2 is equal to 1 over 2 to the 6.43 times, and we'll do times 100, because we're trying to find our percentage, 2 to the 6.43. What we have remaining, if this was 100, is about 1.15978.4. So with this information, I want you to take it and think about what this actually is telling you. Okay, so this is our mathematical calculation. If you're really comfortable working with this equation, work with it. Now I'm going to show you another way before I tell you what exactly the answer is. And that's, look at it as if it was like this. We know about 6 half-lives have undergone. So we have, we're starting at 100, and we go 1 half-life, second half-life, so that becomes 50. Third half-life, 25. Fourth half-life, 12.5. To our fifth half-life, 6.25. And this isn't, I'll explain a little bit more about what I'm doing. And then 1.5625. This isn't actually, I'm sorry, I numbered these a little incorrectly. So this actually goes to this one here. And I just wanted to show a common mistake is that we'll start off 1 as if it was 100, but it's not. This is after the first half-life, this is after the second half-life, this is after the third half-life, this is after the fourth half-life, this is after the fifth half-life, and this is after the sixth half-life. That's 1.5625. Okay? And so we see that, and again, we'll get back to that, the 720 days thing, that is about 6.5 half-lives. We could say then that if we multiplied this times 100, we would get the 100%. Because this is after, because we started at 100, we wouldn't have to multiply it by 100. We would instead call it 100%. So about 1.56% is what would remain of whatever number you have. So using this would be really good if you're very comfortable with using an equation, because this is that 100%, and so you could just know that it's about 1.16%. But this is really good because it shows you pictorially how many the half-lives, what's happening per that 100, and then we know that the answer is about 1.56%. Okay, now because it actually has about a 0.5 more half-life, you're going to want to you could put that in also, and you get something a little closer to 1.172%. But this would put you in a good ballpark figure so that you see what it would be. Okay. This you could use more if you divided this 1 over 2 to the 5th, but this is going to need a better mathematical ability than this one, where we're just saying, okay, first half-life, second half-life, third half-life, fourth half-life, fifth half-life, sixth half-life. If I was doing this on a quiz, I would use this one, and then I would use this one to make sure to check this one, to make sure that I'm in the area of the right answer. Okay? And so that ends the nuclear chemistry video for the quiz 4 review and mid-semester review.